Right. So in this video, we'll look at regularization and we'll look at it from a mathematical point of view and not just like the usual way of people talking about just adding something to the loss function and sum of weights and all that. Let's look at it from a mathematical point of view. This diagram on screen, this is a pretty popular diagram which we keep seeing in a lot of textbooks related to deep learning, and we'll find out why this is the case and how this works and all that stuff. But before that, we need to look at a fundamental mathematical concept. It's called the Lagrangian constraint, right? And the Lagrangian constraint is what mathematically governs the concept of regularization, right? So the general form of writing a Lagrangian constraint is basically minimize f of x subject to, st stands for subject to and not such that, but minimize f of x subject to g of x less than or equal to 0, right? Uh, and when you write this in general form, we can write the Lagrangian like this. The Lagrangian is a two variable function where lambda is the new variable that you introduce. And that is f of x plus lambda g of x, right? Okay, I know that's a lot. So let's like take an example. Let's see what's happening. So let's say we have f of x equals x squared, right? Simple function. We all know what that is, right? It's like a bowl-shaped function. But we are saying subject to x greater than or equal to 1. So we are talking about this region, right? And we are trying to minimize this, right? So how do we do this? I mean, from the graph, it's very intuitive and it's very obvious that the minimum happens here. We cannot plot, let's say, a fifth degree function, right? We can't plot that. So how do we solve this mathematically? The way we do it is, first, let's write it in general form. We mentioned how g of x needs to be less than 0, and here g of x is greater than 1, right? So if I write x minus 1 greater than 0, then I can say that 1 minus x less than equal to 0, and g of x equals 1 minus x, right? So given this, if I write the Lagrangian, it would look something like this, right? X squared plus lambda 1 minus x, right? Now, we know that if we have a function and we want to minimize the function, all we do is we differentiate it and set it to 0. And that's exactly what we'll do to the Lagrangian as well. But what we can notice here is that when x is, let's say, less than 1, right? And x less than 1, we're talking about this region. When x is less than 1, we don't want the function to work properly, right? We want to find a way to penalize when we don't follow this boundary. And that's exactly what this does. When x is, let's say, 0, for example, or let's say minus 1, uh, 1 minus of minus 1 becomes 2. And then we add 2 lambda. So we add more to this function, but we are trying to minimize f of x. So when we add something to a function that we are trying to minimize, we are going against what we are trying to do. And that's what we call the penalty, right? But at the same time, when we look at something that does abide by the constraints, right? For example, x equals 2. 1 minus 2 becomes minus 1, right? And that means x squared minus lambda, right? There we are subtracting something from this function that we are trying to minimize. So we are going along the idea of minimizing, right? Instead of against it. So let's differentiate this and let's see what we get, right? So x squared is 2x and this becomes uh, minus lambda. Now, when we set this to 0, just like how you do to a normal function, we get something like x equals lambda by 2. We are going to set the lowest point. So x equals 1 is the lowest point that we have because we can see that the penalty is directly proportional to x and the value of how it changes with time, right? So we are going to set the lowest value of x, that is 1. And when x equals 1, lambda equals 2. When x equals, let's say, 0, we can see that lambda equals 0 as well. When x equals, let's say, 2, we can see that lambda equals 4, right? So clearly, we can see how penalty which we assign to this value keeps increasing with time. But the idea is x equals 0 is not allowed because our constraint says x should be greater than 1. So we cannot go with this. But you can see how the value of the penalty keeps increasing with time, and that's very obvious, right? Because it's a function that keeps increasing with along. I mean, when I say time, I mean when you move along the x-axis, right? So this is the basic idea of Lagrangians. So the fundamental idea is to get this form where we penalize using the constraint, and the idea is to minimize a function, and we add a penalty term so that when we don't abide by the constraints, we get a penalty, right? Now, what does this have to do with regularization? I'm sure a few of you have probably guessed what we're doing here. So in a loss function, what do? We do MSE, and if we are regularizing, we do lambda and whatever p norm, right? When I say p, it can be anything. It can be one norm, two norm, L1, L2, all that stuff. Now, let's take L1 for example, right? So L1 is right. This is pretty straightforward. And this is the general formula of a P norm. And I think it's pretty straightforward. You can just substitute the value of P, 1 to infinity, zero point 0.5, anything that you want. How does this work? If I draw a very simple example of a coordinate axis. So this is a two neuron example, right? In very simple words. If we have two neurons, each neuron has a weight, and we just add the absolute values of weight. So let's say this is W1 and this is W2. We will see that L1 represents a diamond because modulus represents this region, right? I'm assuming this is some value R. For our sake, we can take 1. L2, in the meantime, represents what that represents is a circle. I mean, the inside of the circle. When we say W1 square plus W2 square, that's basically a circle in the coordinate system, right? And let's say equals 1, and we can equal this to 1 as well. Just for the time being, you can equate it to R or any other variable. We don't need to really do it with a number. I think I've given a basic explanation of how this works. Now with infinity, how does it become a box? This is a very interesting thought experiment that you can actually take home and try out. Because what happens in L infinity is you will basically end up with something like this. Um, you guys can figure out why this works. It's a very interesting thing to think of because when something goes to infinity, we really need to see how the magnitudes start overpowering each other. This is a very interesting thought experiment. Please check it out on your own. In a neural network or in a machine learning algorithm or any of that stuff, right? What are we trying to do? We are trying to minimize this loss function, right? And the loss is basically an MSE or cross entropy or whatever it is that we use. Now, we add this penalty term that is, I mean, we already saw how it works, right? It's a Lagrangian. We add this penalty term to the MSE so that we can have a certain constraint on the loss, which is also a function of our weights. This is how we prevent our weights from exploding and overfitting and things like that. We want to find a loss, but we also want our weights to be inside this region, right? When we're talking about L1. When we're talking about L2, we want to find a loss, but not just any loss. We want our weights to be inside this region. So what happens is initially you have some loss, right? And that's your MSE value. So it can be anything. But we won't accept that value because the weights will not lie in our desired region. So it suddenly becomes an invalid loss. How that's similar is, for example, in this case, we cannot choose x equals 0. Even though x equals 0 is the minimum of the function, we cannot choose that because we have set a constraint that x needs to be greater than or equal to 1. Similarly, we cannot choose an MSE that is just a minimum, that just minimizes the loss. And we cannot choose that just because it's a very low value. We are putting a constraint using our weights that it needs to be inside this desired region. This allows for more uniformity. Okay, let's also check out one thing before we go further. Now, the gradient of L1 would be sine of W, and the gradient of L2 would be 2W, right? The reason is, in our case, it is sine of W1 plus sine of W2. That's because if anyone's interested, d by dx of modulus x is equal to sine of x. Okay, and this is because d by dx of x square equals 2x. So here it would be 2w1 plus 2w2. Again, if you're multiplying lambda, that comes here, obviously, right? It's a common function. What happens is we need to minimize this loss, that is your MSE or cross entropy or something, but at the same time, we need to abide by these constraints. So what happens is our loss, let's say initially it's some value, but we cannot take that value. So we try to go to another place, and maybe that still doesn't work out. And when we keep trying this, what happens and what we notice generally in machine learning is that L1 leads to sparse solutions. What does that mean? That means generally one or multiple parameters would be set to zero. That is, the loss function most likely would intersect either here or here or here or here. Random statistics and probability says that it is much more likely for your loss function to choose one of these 4 points instead of one of the points on the line, right? With a circle, all the points are equally probable. So your loss function might come here or here or here or here, or any of these points. Any point, all points are equally likely. But when it comes to a diamond, these points are clearly more biased and have clearly more probability. So that is why we say that L1 leads to sparse solutions. Because if we choose one of these corners, either W1 would be equal to 0 or W2 would be equal to 0. But when we go to L2, we have more dense solutions. That is both W1 not equal to 0 and W2 is not equal to 0 as well. This is because, again, as I said, according to random statistics, the intersection happens with less probability along the edges in a diamond and with equal probability on all parts of a circle, right? So we can think of regularization as a tug of war. It's a tug of war between your loss and your constraint. And it's a push and pull. And it's about how much compromise do you make to decrease your loss. And that is where the idea of intersection comes in, right? So this is a basic overview of how the loss function and regularization work together to do something called as constrained optimization according to mathematics, right? And this is a very low dimensional example of the math that takes place behind the scenes, which a lot of people don't really talk about when it comes to regularization. We just say that, oh, we add the weights, sum of weights, modulus of weights, or whatever. And an interesting thing for you guys to take home is to find out how the infinite norm is calculated and why it is a square box. I've already explained to you how L1 is a diamond and L2 is a circle. You guys can check that out. And that is pretty much it for this video. Peace.